Hi guys, this is a video solution to example sheet 9, which is this one, and there are 7 questions. As usual, I will go through every single one of them and give you a detailed solution. So once again, this is on top of the typed solutions, which you can find on the course website. So let's start with question 1. So you have a sample of 81 students. The sample mean of the scores is 74.6 and the sample standard deviation is 11.3. And we want to find the 90% confidence interval for the population mean. Right, so let's see how we can do that. So this is question 1. So let's write down what we have. We have n equal to 81. We have x bar equal to 74.6, and we have s, the sample standard deviation, equal to 11.3. And we want to find 90%, which means 100 times 1 minus alpha is 90. Okay, and so this implies that 1 minus alpha is 0.9, alpha is 0.1. All right. In this case, clearly, what the formula, if you look at the notes, guys, or the videos, you will see the formula that you need to use is the following. This is the formula that I gave you guys, that when the population variance or the population standard deviation is not known, this is the 100 times 1 minus alpha confidence interval. But in this case, the sample size n is pretty large. 81 is a large number. At least in statistics, anything above 25 is considered large, right? So instead of using this formula, you can also use the following approximation, which is right, since n is large, right? Remember that one of the properties I mentioned in this video on students' t distribution is that as n approaches infinity, this approaches the standard normal, and what you have here is the percentile of a standard normal. Okay, and this is the percentile of a t distribution with n minus 1 degree. So this is the formula that I'm going to use now. Okay, so let me put this in a box. Okay. Alright, so your x bar in this case is 74.6 plus or minus z 1 minus alpha by 2 will be 1 minus 0.05, which is 0.95. Alright, s is 11.3, n is 81. Okay. Now this you can read off the table, and if you read this off the table, you will get 74.6 plus or minus 1.6449 multiplied by 11.3 divided by the square root of 81 is 9. Okay. Now, if you work this out using a calculator, this is what you will get. So the lower limit will be 72.53, and the upper limit is 76.67. So this is the 90% confidence interval for the population mean score. Okay. Now let's go to question 2. There's two parts. So here you have a sample of 30 from a normal population, and the sum of the data is this, and the sum of the squares of the data is this. I want to find a 95% confidence interval for mu, assuming that the population variance is this, and also confidence interval for these two when both are unknown. Let's see how we can do this. So let's, question 2, part 1. We are assuming sigma squared. So let's write down what we have. We have n equal to 30. We have sigma squared equal to 30. So sigma is the square root of that. And we want to find the 100 times equal to 95% confidence interval. So that implies that 100 times 1 minus alpha is 0.05, sorry, 0.95. So alpha is 0.05. Now we also need x bar. Remember, x bar is the sample mean. So this is simply 1 over 30 times the sum of the xi's. Now we are given the sum of xi, which is this number here. So this is 1568 divided by 30. Yeah. And if you do the math, you will get 52.2817. Now the formula that I'm going to use, because we are assuming that sigma is known, or sigma squared is known, the formula is this: x bar plus or minus z 1 minus alpha by 2 sigma divided by root of that. Alright? So this will be x bar is 52.2817 plus or minus. This guy here is z 0.975. Sigma is square root of 30, and is also 30, so square root of 30. Right, so this will be 52.2817 plus or minus. This guy, if you read off the table, you will get this to be 1.96. Right, and these two cancel. Okay, so the final answer for part 1 is the following. It's going to be 50.32, the lower limit. The upper limit is 54.24. Alright, so this completes the first part of question 2. Now, the second part, we want to find confidence intervals for mu and sigma squared when both are unknown, right? So let's start with the confidence interval for mu first, right? Now you may recall the formula involves s, the sample standard deviation. So we need to compute that first. Now, one of the formulas I gave you in the video and the notes for s squared is the following. You probably remember that I even gave a proof of this formula, right? Now, for n equal to 30, this becomes 1 over 29. And this guy is given to us here as equal to this number, so it's 83006.73. N is given to us as 30. X bar, we know what it is. It's 52 point. Right? Now, if you work this out, guys, you will get 34.67. So this is the sample variance. So now we can use the formula for, so the CI, the confidence interval for mu is x bar, right, plus or minus t, the percentile of t, at 1 minus alpha by 2, right, times s divided by root of n. If you look back in the notes, you will see this is the formula I gave you. So x bar, we know what it is equal to 52.2817 plus or minus t, when alpha is 0.05, so this is going to be 0.975 with a degree of freedom of n minus 1, which is 29, times s we have is the square root of that, which is the square root of 34.67, and n is 30, right? Right, this guy here you can read off the table for the t distribution which I gave you. I mean, I showed you how to read that in one of the videos, the video on t distribution. So you should know how to read it. So this will be 52.2817 plus or minus. If you read this, you will get 2.0452 multiplied by 34.67 divided by the square root of 30. Right now, you should, this confidence interval, you should do the math, will be 50.09 is the lower limit, 54.48 is the upper limit. All right, so this is one of the things we need to do in the second part. Now the next thing we need to do is to find the confidence interval for sigma squared. Now you may recall from the notes that the confidence interval for sigma squared is, this is what I gave you in the notes. Chi squared with n minus 1 degree of freedom, and if you look in the look at the notes or the videos, you will see this. Alright, so this is the formula for the confidence interval for. Okay. Right now, if you sub in the numbers, we know what s squared is, we know what m is, so this is going to be 29 multiplied by s squared, which is 34.67. Alpha is 0.05, so this is going to be chi squared 0.975 with a degree of freedom of 29. Alpha by 2 is 0.025 with a degree of freedom of 29. Alright. You can read these two guys from the table for the chi-square distribution, which I showed you how to read that in the video on chi-square distribution. So you should look at the video on chi-square. You will see. You should be able to read these two. So if you do that, this is what you will get. Okay. Now, doing the simplification, doing the math, this will come. The lower limit will be 21.99, and the upper limit will be 62.66. All right. So this completes question 2. All right. Next, question 3. You need zoom it in. This. All right, here you have a random sample of 500 households. 80 were found to have 3 or more TV sets. Find an approximate confidence, 90% confidence interval for the proportion of households having 3 or more TV sets. Right, so this is a question on proportions. Now you may recall you may recall that the confidence interval for P that I gave you in the notes and the videos is the following. It's an approximate confidence interval. Where X bar denotes the sample proportion. Alright, so this is you should remember this formula from the notes or the video. So this is what I'm going to use over here. So let's see what we are given. We are told that N is 500, right? And out of that 80 have 3 or more TV sets. So your X bar, the sample proportion, is 80 divided by 500. Okay? So which is 0.16. And your alpha, we want 90%. So 100 times 1 minus alpha is 90. So 1 minus alpha is 0.9. And your alpha will be 0.1. Alright. Okay guys, so hence the CI is X bar, which is 0.16 plus or minus Z 1 minus alpha by 2, which is 1 minus 0.05. X bar is 0.16 times 1 minus 0.16. Oh, sorry, I forgot to put this sign. There should be a square root sign which I forgot to put, excuse me. Divided by n, which is 500. So this is square root of this whole thing. Okay, so this will be 0.16. Z at 0.95 is 1.6449 multiplied by 0.16 times 0.84, right, divided by 500. Everything in square root here, right? Okay, now if you work this out using a calculator, this is what you will get. Alright, so that completes the answer for question 3. Right, now let's move on to question 4. It has several parts. Alright, so here you have a sample from a normal where mu is unknown but sigma is known. What is the width of the confidence interval for mu? What variable quantities affect this width? Then for sigma equal to 10, tabulate the widths of the confidence interval for mu when n is this and alpha is this. Okay, let's see how we can do this. So, question 4. The confidence interval for mu when sigma is known is the following: is x bar plus or minus right. I'm sure all of you know this by now. Okay. Now in this question we are talking about the width of the confidence interval for mu. So the width is going to be remember, the width is the upper limit minus the lower limit. So it's simply x bar plus okay. Alright, now we should calculate this. This reduces to 2 times z1 minus alpha by 2 times sigma by root of n. Alright, so this is the width of the confidence interval. Now the question is, which variable quantities affect this width? Obviously alpha will affect the width, right? And sigma will affect the width, and n will affect the width. So let's see how we. So let me create a column, say where called variable, and let me create another column called effect. How the width is affected. Okay, on width. Okay, the effect on width. All right, now let me put the 3 variables, which are alpha, sigma, and n. Now let's see if alpha increases. Remember, alpha is a number between 0 and 1, right? So if alpha increases towards 1, right, then this is going to get smaller, right? This is, so as alpha increases towards 1, this will get smaller and smaller and smaller. So z of this will be also get smaller. So as alpha as alpha increases, right? Towards, say, suppose it increases towards 1, right? Then this is going to get smaller and smaller and smaller. The smallest value you can take is half, right? Because if alpha is 1, right, 1 minus half is half, and z at half is 0, right? Okay, so this decreases. Okay, so So the width decreases too. Okay, so that's for alpha. Let me put a line here just to make a distinction so that you don't get confused. Right, so this is for alpha. Now, as sigma increases, this whole thing is an increasing function of sigma, so the width will increase. Okay. All right. And finally, as n increases, because you have n in the denominator, and as n increases, this will decrease. So as n increases, the width will decrease. All right. So this table here illustrates. This table illustrates the effect of each of the three variables, alpha, sigma, and n, on the width of the confidence interval. Right? So that's one thing we need to do. The other thing is tabulate the width of the confidence interval for these values of n and these values of alpha. Alright, so let's see how we can do that. So I need to create another table. So suppose this is alpha is 0.1. Suppose this is 0.1. Then we have different values for n equal to 5, n equal to 15, n equal to 30, n equal to 50, and n equal to 100. Okay. So this is a table. Now what I'm going to do is, in this table, I'm going to, for each combination of alpha and n, and taking sigma to be 10, right? So we are assuming sigma is 10. So for each combination, I'm going to compute this formula here. Right? So this is what you will get for this 14.71, 8.49, 6.01, Alright, so these are the values that you will get from using this formula here. Right. Alright, the next thing we want to do is to do a plot of this. Okay. So if you plot these on a graph, right, you will see this. This is what you will get. So there are two different curves here. This curve corresponds to alpha equal to 0.01. This one corresponds to alpha equal to 0.1. And the x-axis is the values for n. The y-axis is the width of the confidence interval given by this formula here. Right? So you can see that as n increases, the width decreases. That is exactly what I said here. As n increases, the width will decrease, right? And you also see that as alpha increases from, say, 0.01 to 0.1, right? The width of the interval decreases, and that's exactly what I said. As alpha increases, the width decreases. All right. Okay, guys. So this completes the answer to question 4. All right. Right now, let's move on to the next question, question 5. Okay, let me zoom in just a minute, guys, right here. So here the reaction times are normally distributed with sigma equal to 0.05, and what are the number of measurements she must take so that a 95% and 99% confidence interval for the mean time has a width not exceeding 0.02. Okay. All right. So this is not difficult. So this is question 5, guys. Now remember the CI, the confidence interval for mu, as I said in the previous question, is this is the confidence interval for mu. So the width of this confidence interval, as I said before, is 2 times okay. Right, now we are told that sigma is equal to 0.05, so this is going to be 2 times okay, which is equal to 0.1 okay. Now we want this not to exceed 0.02. Okay, so we want this to be less than or equal to 0.02, right? All right, so which means that root of n has to be greater than or equal to, sorry, excuse me, guys. Root of n has to be greater than or equal to 0.1 divided by 0.02 times Z1 minus alpha by 2, right? Okay, so this is the same as saying that root of n is greater than or equal to 5 times this. Okay. Now if you square both sides, if you take the square of both sides, this becomes n, and the square of this is 25 multiplied by okay. So this is what we want. Now we need to consider 2 cases. We need to consider the case where, excuse me, where alpha is 95%. Alpha is 95%, and the case where alpha 100 times 1 minus alpha is 99%. So let's consider the first case where 100 is equal to 95%. Okay, so this implies that Okay. So Z becomes, okay, and this becomes, if you read this off the table, this will become 1.96. Alright, so if you call this say star, star implies, star is the same as n greater than or equal to 25 multiplied by 1.96 squared, right? Which is approximately equal to 96.04. So you would say that the sample size should be greater than or equal to 97, because you cannot have a sample size like this. So the minimum sample size should be, be 97. Okay. So that's part 1. Part 2, we want 100 times 1 minus alpha to be 99. So this implies that okay, so your alpha, okay, so your Z 1 minus alpha by 2 will be Z 0.995, which is approximately, I think is 2.58 approximately, right? So the star will become n greater than or equal to 25 times squared, and this is equal to 166.41. So therefore the minimum sample size should be 167. Alright, so this completes question 5. Okay, now let's go to the next one, which is question 6. Let me zoom in slide. So here both mu and sigma squared are unknown. You have a sample of size 30. With sample mean this is the sample variance. You want to find a 98% confidence interval for mu and a 98% confidence interval for sigma squared. Right. Okay, so in this case, let's start with the confidence interval for mu. The confidence interval for mu when sigma squared is unknown is the following: is x bar plus or minus t with n minus 1 degree of freedom s divided by root of n. Okay, so this will become, if you sub in the numbers, you have x bar equal to 127.442 plus or minus, your alpha is 98, so your 1 minus alpha by 2 will be, sorry, 100 times 1 minus alpha is 98, right? So your alpha will be 0.02, right? Okay, so your alpha by 2 will be 0.01. So this will be 0.99. right, with n is 30, so this is 29. Okay, and s is the square root of 228.661 and divided by the square root of 30. Okay. Alright, now this you can read of the table for the t-distribution. You will get it to be 2.462 multiplied by Alright, so this will become, if you do the math, the lower limit will be 100, the upper limit will be, you do this. Alright. Okay guys, so that's the first part. The second part is that we want to find a 98% confidence interval for sigma squared. Right? Okay, so let's see. Okay, for the first thing is to write down the formula, which you should know. Alright. Okay, so okay, now let's sub in the numbers. N is 30. Right? You can read this is the question, guys. N is equal to 30. So it's 29 times s squared is 228.661 divided by chi squared with n minus 1 degree of freedom. Right, let me put this here. Chi squared with alpha is, we know 100 times 1 minus alpha is 98, so alpha should be 0.02, right? So 1 minus alpha by 2 is 0. This, okay? N minus 1 is 29. Okay, now you should simplify this, you should do the math. Before you do that, let me read the values for this and this of the chi squared table, which I showed you how to do that. So this, if you read from the table, it will be 49.588. And this, if you read the table, will be 14.256. Okay. All right. Now, if you do the math, it will be 1333.73. That's the lower limit. The upper limit is 465.15. Alright, so that completes question 6. Let's do the last one, which is question 7. It has 4 different parts. Okay, start with the, so you have a sample from a normal distribution with these parameters, and y is this, ax plus b, and you have this. Show that this is equal to this and this is equal to this, right? Alright, so this is question 7, part 1. So we are told that y is equal to ax plus b for every x and every y. Now remember, the mean of the normal distribution is the expectation. So mu y, right, which is the mean for y, is the expectation of y. This is the expectation of ax plus b, and this is 8 times the expectation of x plus b. Now the expectation of x is the mean for the y. It's a mean for the distribution of x, right, which is also normal. So this is, alright, so we have shown that mu y equal to a mu x plus b. Alright, now to show, look at the variance. This is the variance of the normal distribution, the variance of the random variable. So it's the variance of y. This is the variance of ax plus b. Now the variance of this, I'm sure you know, is a squared times the variance of x. Now the variance of x is the variance of the normal distribution which x has, right? So this is a squared times sigma x squared, right? So it's not difficult, is it? So that proves the first part of question 7. Part 2, we want to show that y bar is equal to ax bar plus b, and sy squared, which is the sample mean for the y's, is equal to a squared times sx squared, where it's sx squared is the sample mean for the sample variance for the x. Sy squared is the sample variance for the y's. X bar is the sample mean for the x's, and y bar is the sample mean for the y's. Right. Alright, now let's see how we can do this. So let's start with the y bar, right, with the sample mean for the y's, which is by definition is the this is the definition of sample mean. So this is 1 over n times, we know that y equal to x I plus b. Okay, so we should take the sum inside. This will be alright guys, so this will be 1 over n times 8 times the sum of xi. Now the sum of b is a constant, so it's going to be n times b. Now if you take the n inside, this will be 8 times 1 over n times the sum of xi. And the n and the n here cancel, so this will be b. Okay, now this guy here is the sample mean for the x's, so this is ax bar plus b as required. Alright, so that's the first part of part 2. The second part of part 2 is to show that sy squared, which is the sample variance for the y's, is equal to a squared times the sx squared, which is the sample variance for the x's. Right. So let's see. So this is part 2 of question 7 continued. So we want to start with sy squared, which is the which is this, right, by definition. Okay. Now we know that yr is equal to plus b, and we know from part 2 earlier that y bar is ax bar plus b, so minus y bar is minus ax bar minus b. Okay, so these two guys cancel out. Okay, and a is a common factor, so you can pull it outside. So you get a squared times 1 over n minus 1 okay. Now what you have here is the sample variance for the x's. So this is x a squared times 2 sx squared. So that completes part 2 of question 7. Part 3 is this. You have a confidence interval for mu, which is denoted by this, and a confidence interval for mu y, which is denoted by this. The question is to show that this is equal to this. Excuse me. So, right. Let's see how we can do that. So we are given a confidence interval for mu x, right? Which is this one, lx comma ux, right? So L stands for lower limit, U stands for upper limit. So this means that the following, that the probability that the probability that mu x lies between the lower limit and the upper limit is equal to 100 times 1 minus alpha. Right? Now what I'm going to do is the following. I'm going to do a multiplication and the division. So the first thing I'm going to do is I'm going to multiply the three numbers here by a. And the next thing I'm going to do is I'm going to add a b to each of these three numbers. So this will become right. Okay. Now we know from part 1 of this question that this guy here, the middle term must be mu y. Right? Okay. So what you have here is a statement on mu y. So it says that the probability that mu y lies between these two is 1 minus alpha. So hence, the interval from right, so this interval that from the lower limit to the upper limit must be 100 times 1 minus alpha, confidence interval for mu y. But we are told at the beginning of the question that this is a confidence interval for mu y. Right, so hence the confidence interval for mu y, which is Ly u, must be equal to, okay, to this. Okay, so that completes part 3 of question 7. Now part 4 is similar. So here we have a confidence interval for sigma x squared and a confidence interval for sigma y squared. So we want to show that this is equal to this. So the process is very similar. So you have a CI for sigma x squared is okay, and this means the following, that the probability that right, now next thing I'm going to do is I'm going to multiply every term here by a squared, right? So this will be the probability that a squared sorry, what am I doing? It's less than equal to a squared Now this guy here we know is from the first part of this question. We know that a squared times sigma x squared is sigma y squared. So hence so this is a statement on sigma y squared being between these two with probability 1 minus alpha. So hence But we are told in the question that the confidence interval for sigma y squared is given by this. So hence the given confidence interval, which is Vy, Wy, right, must be equal to this. Okay. All right. So this completes the solution to question 7. And also completes the solution to tutorial sheet 9.